Right, hello grade 12s. We are starting a brand new section today, and that section is probability. Please remember probability is going to be done in your paper 1 book because it is paper 1 content. Today we're going to look at grade 11 revision. The first section of the grade 11 revision is something called probability diagrams. So probability diagrams, there are 3 basic probability diagrams you need to know very well from grade 10 and grade 11. The first one is your tree diagram. Now, tree diagrams can either be used with independent or events, independent events or events that are not independent. And it doesn't really matter whether they are independent or not when you multiply. We'll talk about that multiplication just later. It has more to do with the fact that if the two events are independent, it means whatever happens on the first event has no bearing on what happens with the second event. Whereas if the events are not independent, it means whatever happens on the first event will have an influence on the second event. Now in grade 10 we mostly did events that were independent. In other words, the probabilities on the first event stayed exactly the same for the second event. Whereas in grade 11 we mostly did events that were not independent. So whatever happened on the first event then had an influence on the second event. Now please remember, tree diagrams are ideally suited for something called consecutive events. In other words, events that follow on one another. So first the one thing happens and then the second thing happens. Like for instance, you throw a die and then you throw a die again. So first the first event and then the second event. Okay, so that is where tree diagram is ideally suited. Obviously you can use it for 2 events following each other, 3 events following each other, but mostly it's used for events that follow each other. Okay, so let's look at an example of the grade 11 one where the events are not necessarily independent. Now this one says the probability that the first answer in a maths quiz competition is correct is 0.62. If the first answer is correct, the probability of getting the next answer correct is 0.78. So getting the next answer correct is dependent on whether you get the first answer correct, that probability right there. And then if the first answer is wrong, the probability of getting the next answer correct is 0.35. So that probability is dependent on getting the first one wrong. So this is why these events are not independent. What happens on the first one does influence the probabilities on the second one, so you have to watch that. Determine the probability of getting the second answer wrong. So putting together this tree diagram, we're going to start off by saying, obviously you can either get the answer correct or you can get the answer wrong. And then the second question, again, you can either get it correct or wrong. And there you can also either get it correct or you can get it wrong. So if you then say the probability of getting the first answer correct is 0.62, so getting the first answer correct 0.62, then because that event is split up into only 2 possibilities, correct or wrong, then those 2 probabilities must always add up to 1. That is very important with a tree diagram. If an event is split up into 3 possible outcomes, for instance, then you have to add all 3 the branches probabilities together to form 1. But very important, each one as it splits up has to add up to 1. Okay, so that is why if this is 0.62, this one is going to be 0.38. So as I said, if the first answer is correct, the probability of getting the next answer correct is then 0.78. So there I can put 0.78 because that is dependent on getting the first answer correct. But I can't put 0.78 there again because, like I said, these events are not independent. If the first answer is wrong, the probability of getting the next answer correct is 0.35. So that's the probability I put over there. This one is then going to be 0.35. And again, like I said to you before, if an event is split up into 2 possible outcomes, then I must add those 2 probabilities and that will add up to 1. So if this is 0.78, this is 0.22 to add up to 1. And if this is 0.35, this is 0.65 to add up to 1. Okay. Now, in spite of the fact that these events are not independent, I'm still allowed to use multiplication here. Please do not go and confuse what happens in a tree diagram with the later definition we're going to be doing about independence. In a tree diagram, I fix the probabilities to suit the first outcome. And because I fix the second set of probabilities to suit the first one, I'm always allowed to multiply. And when I say multiply, I mean this one where I say getting the first answer correct and so multiply getting the second answer correct. So the moment I fix these probabilities, I'm allowed to multiply. Okay, right, now the question says determine the probability of getting the second answer wrong. So getting that second answer wrong, there is getting the second answer wrong, or there is getting the second answer wrong. So I can get it correct and wrong, or first answer wrong and second one wrong. So that's my and this is my or. And please remember, when I say and, I multiply, and when I say or, I add. So I'm then going to say it's the probability of getting the first answer correct and multiply getting the second answer wrong, which is 0.22. Or, so plus the probability of getting the first answer wrong, 0.38, and multiply getting the second answer wrong, 0.65. And that then, if I calculate this, is going to be the probability of getting the second answer wrong. So 0.62 times 0.22 plus 0.38 times 0.65. There we go. And that will give me 0.3834. Please note that generally what they do is they say at the beginning of every maths paper 1, they say please round your answer off to 1 decimal place unless the question states otherwise. Generally, when it comes to probability, we don't like rounding off to only 1 decimal place because that is incredibly inaccurate. So please read the question carefully so you can see what they want in terms of rounding off. Okay, so those were the first probability diagrams, tree diagrams, which work very well for consecutive events. In other words, events that follow on one another. Okay, now the second one we have are Venn diagrams. Now Venn diagrams are quite lovely because Venn diagrams, you can represent probabilities on a Venn diagram, or you can represent sets, in other words, the number of elements in a set on the Venn diagram. So first we can talk about how to use Venn diagrams to represent probabilities. So when you go and you color certain sections in a Venn diagram, that colored in section represents a specific probability. So we have discussed this with you guys last year, but let's just jog your memory. Now this one specifically refers to the intersection between set A and set B. We also refer to the intersection as the word and. So I can say this is the probability of A and B. So like I said, that sign right there represents and, or the intersection. So that's the overlap between the two sets. Now this one is not the overlap. That's everything in A, everything in B, not doubling up the middle, because you never double up the middle. So that means everything in A, everything in B. We use the word or because it can either be in A or it can be in B. So this one we say it's the probability of A or B. So that sign right there represents or. We also refer to it as the union of A and B. Then this particular one looks super complicated until you realize I've colored in everything except A. A is not colored in. So because A is not colored in, what I've got here is the complement of A. This is everything that is not in A. So please remember that stands for the complement of A. The complement of A. So that's everything that is not in A. And then the last one I've got colored in there, a little bit of a tricky one. Let's see if you remember this one. This one is everything that is in A, but it must not be in B. So it's literally everything that is in A and not in B. So it's the probability of being in A and not in B. This is a very common one. That's a very common one to describe this little bit. By the way, if I had only colored in that little bit, that would have been everything that is in B and not in A. So you can go and revise these things from last year. We did go and we spent some time on getting these Venn diagrams right. I know this is a very quick recap, but just to remind you of the most important ones. Right, so now we can also go and we can take Venn diagrams and use it to represent the number of elements in a set. So this one doesn't necessarily represent probabilities. These are the number of elements in a set. So in this example, they say a survey was conducted amongst 110 learners. 54 learners do one-act plays, 38 do choir, 29 do debating, 15 do only choir, 20 do one-act plays and debating, 11 do choir and debating, 4 learners do all three. And then they ask, what is the probability that a randomly chosen learner does only one activity? Now, in order to answer this question, we first have to represent this information on a Venn diagram. And generally here, they will ask for a Venn diagram. But a Venn diagram is perfect for this one, simply because we are going to divide into separate sets. So the moment you go and you say something can be in this, or it can be in that, it could also be in that and in that, then a Venn diagram is ideally suited as a probability diagram. Okay, so please remember, and we did say this very, very clearly last year, never ever start with 52 learners do one-act plays. Because the problem is, if you look at over here at my sets, and I've divided it up into one-act plays, choir, and debating, then if there are 54 learners that do one-act plays, they can go in here, which are the learners that only do one-act plays, over here, which are the learners that do one-act plays and choir but not debating, over there, which are the learners that do one-act plays and debating but not choir, and over there, the learners that do all of them. So that's why you can never start with that 54, just simply because it needs to be split up into 1, 2, 3, 4 spaces, and currently I don't know what goes where. You always have to work from the inside and go out. Please remembering to subtract as you move out. So that is why we always start with the inside, which is this one, 4 learners do all 3. So I can put 4 over here. Those are the 4 learners that do all 3 of those activities. And I can tick it off here, say, good, I've got that. Then I will go for the other overlaps before I start going for these ones. So the other overlaps that they've got is 11 do choir and debating. So choir and debating is over there. But now be careful. Those 11 learners that do choir and debating are split up into 2 spaces. And there's already 4 over there, which means over there I need 7. Because 4 plus 7 adds up to the 11 that do choir and debating. Then I go to the next one. 20 do one-act plays and debating. So I go to one-act plays and debating, which is over there. Now that means this is the part for one-act plays and debating. Again, it's split up into 2 spaces. I've got 4 there already. This needs to be 16. So that's 16 plus 4 give me the 20 for that one. Now the next one I have is they say 15 learners do only choir. So 15 learners do only choir. I can go to choir, and this is the space of the learners that do only choir. So I can put 15 over here. Right, so now I can keep moving and I can say, okay, we look at the learners that do one-act plays. So the learners that do one-act plays, that's 54. But as you can see, we still have 2 spaces over there left over. So I can't currently put that one in. Then we look at the 38 learners that do choir. I've already got those 3 spaces, which means I can now get this one. Simply by saying the total for choir must be 38. But there's already a 4, a 7, and a 15. So I subtract that. So I go minus 4, minus 7, minus 15. And that's going to give me 12 that go over there. So all of those add up to the 38 learners that do choir. So I can tick that one off. Then I can actually now go back to the 54 learners that do one-act plays. And I can say, okay, I know the total of those 4 spaces is 54. So I can say 54 minus 12 minus 4 minus 16, which is going to give me 22 learners that do only one-act plays. So I've used this one. Now I can go to the 29 learners who do debating. So currently I know there's 16, 4 and 7 there, so that 16, 4 and 7 is 27, which means there's only going to be 2 over there to add up to the 29. Not done yet, because they told me up here that there are 110 learners in total. So because there are 110 learners in total, I will now have to go and subtract. I'd have to go 110 minus all of that, which is currently there. So let's just do that one. 110 minus 22 minus, let's say, 12 and then 15. Then 27, because that's 16 plus 4 and 7 is 27, minus 2. And that's going to give me 32 that I can put outside here. Those are the 32 of the 110 learners that clearly didn't do any of those events. Now I'm not done, because I still need to answer the question. The question said, or asked, what is the probability that a randomly chosen learner does only one activity? So only one activity, if you think about it, happens over here. It's all the learners that only do the play acting. So the one that plays, 22. There are the learners who only do choir, so those 15. And there are the learners that only do debating, so those 2. So it's going to be 22 plus 15 plus 2 out of the total of 110 learners. Now you could have done it separately. You could have said 22 over 110 plus 15 over 110 plus 2 over 110, because we use the word or, but it's just easier to do it like this, to just add them up, because you get exactly the same answer. So we're going to now go and say that's 22 plus 15 plus 2 over 110, which gives me 0.3545. I'm just going to round it off to 4 decimal places. Normally we generally stick to 2 decimal places, but just to make it more accurate, 4 decimal places. Okay, so those are my Venn diagrams. Please remember, in the Venn diagram, start on the inside and work your way out. Otherwise you're going to be in a big mess. It's going to be horribly wrong. Now, the last of our probability diagrams are our contingency tables. So our contingency tables are tables where we divide up the information into different categories or classes. But those categories, normally the ones that go in rows, are very similar, and then the categories that go in columns are very similar. So that's why generally they call it a two-way contingency table, because you divide into categories in 2 directions. So horizontally in the rows and vertically in the columns. So this one says, passengers on a flight choose only one beverage as indicated below. And then the very first question, let's just talk about this quickly. So we have male and female passengers on this flight, so divided up, 60 male passengers, 100 female passengers, and those male and female passengers could only choose one drink. So that's why they could choose tea, coffee, or fruit juice. Now the first one they say determine A, which is pretty easy and straightforward, because that column plus that column total must add up to A, and those 3 row totals must add up to A. So I can either go 60 plus 100 is 160, or I could have gone like this, 80 plus 20 is 100 plus 60 is 160. So that's pretty easy and straightforward. Now the next one says, determine the probability that a randomly selected passenger is female and chose T. So we need a female passenger who chose T, which is right over there. Those 40 passengers out of the 160 were female and they chose T. So I can say that's 40 out of 160. I'm not going to simplify that. I'm actually going to leave it in that format. If you do want to put it in simplest fraction form, so in other words, if you want to type this in and you want to say 40 over 160 is going to give you 1 over 4, that's absolutely fine. But technically speaking, you don't even really have to do that. Okay, so now this is where it gets slightly trickier. They say, given that the event of a passenger choosing coffee is independent of being a male, calculate B. Now this word independent we're going to discuss a little bit later on. So we're going to discuss a little bit later on. So I'm going to just quickly talk you through it. But if you are confused as to why I do this, in the next video I'm going to talk about mutually exclusive events and independent events, and then hopefully that'll jog your memory on this one. So we're saying the event of a passenger choosing coffee, so choosing coffee there is going to be 80 because choosing coffee, there are 80 people that chose coffee out of 160. So that's the probability of choosing coffee. Is independent of being a male. So I have to now go and see where is being a male. So being a male is right over there. All of these are then males. So I know that being male is then going to be equal to 60 out of 160. Okay, so what we have here is we have the probability of drinking coffee, and what we have here is the probability of being male. But according to the definition of independence, if the probability of being male is independent of the probability of being coffee, then the probability of being male times the probability of drinking coffee is going to be equal to the probability of being male and drinking coffee. So I've got that 80 over 160, I can write that down. I've got that 60 over 160, I can write that down. And then I need to go and see where's the probability of being male and drinking coffee. So being male and drinking coffee is right over there. That's B. So B is male and drinking coffee out of the total of 160. So I can say it's B over 160, which then allows me to solve for B. I've got an equation set up that I can solve for B. So I can then say it's that 80 over 160 multiplied by 60 over 160, and then divide that, multiply that by 160 to get to B. So times 160 is then going to give me 30. So using the definition of independence, I can then calculate the value of B. Okay, so I can go back to this and I can say I worked out A, that's 160. I've now worked out B, that's equal to 30. So let's look at the next question. The next question then says, determine the probability of a passenger who chose coffee being female. Now, this is one we did discuss last year, where we said that we have a given probability. Okay, so we call this a conditional probability, meaning determine the probability of a passenger who chose coffee being female. That is my condition. We know that this passenger chose coffee, and because this passenger chose coffee, I can only look at the coffee drinking passengers who are female. So because it says who chose coffee, I will now go and I will eliminate all the other passengers that didn't drink coffee. So I'll only look at this row. So very important, I'll highlight this one. Only this row because it's condition. It's only the coffee drinkers. So obviously I need to now go and say, what is the probability that a given coffee drinker was female? So that's going to be this value C out of 80, not out of 160, because it's not all the passenger, it's only the coffee drinking passengers. So obviously this one is going to be equal to 80 minus 30, which is 50. So I first have to calculate that, and then my probability here, my conditional probability here, is 50 out of 80. And again, I can just simplify that to 5 over 8. I can actually leave it like that. Okay, so this is pretty much your probability diagrams. Thank you very much for listening. There will be a second video just talking about independent events, which is something we need to discuss after this previous example. And then we also need to talk about mutually exclusive events and complements. Thank you very much for listening.